Um, it doesn't matter which way to me, as long as you can get it back to your paper and you understand what it is. The most important thing in your calculator is your scale. Your scale on it, that little triangle, the delta table that you're looking for, even in a delta scale, when you do it on your graph, that's what relates to your four quadrants. Not the period, but the quadrants. So we'll take a look at those. Now your cosine curve works like your sine curve does off your quadrants. These are your mins, your maxes, and your zeros. So again, we go around your quadrants to sketch this. Remember, we're sketching. So we're not like exact measuring all those little angles in between, but we're sketching. And a good way to sketch is by your mins and your maxes and where your zeros are. So if we pull out your cosine, which is your x, it goes in a pattern of 1, 0, -1, 0, 1. And it would make sense that if your sine started at 0, your cosine can't start at 0, right? The only numbers on your quadrants are zeros and ones. So your cosine has to start at your 1. Then 0, then the -1, then the 0, then the 1. Again, it's a continuous curve just like your sine curve is. And I know, yes, you know this part. But just to like put it together, we know our domain stays the same as your sine curve, all real numbers, and your range also stays the same. And then all the little decimals that come in between, we don't have to worry about because we're sketching and we need to hit our mins and maxes and where we cross the x-axis. Okay? Now, if you do any transformations, you do them the same way off of this. So say you're doing y equals cosine 2x, and you're changing your frequency. Your frequency is now 2, which tells us we have 2 complete cycles in 2 pi, or 2 complete cycles in 360. That means every 180 we complete a cycle, right? That means within this 180, we need 4 quadrants. So again, we section these into 4 quadrants. Same thing we did with your sine curve. And we start at the 1, at the 0, at the -1, at the 0, at the 1. This gives us 1 cycle. I can write it sideways. Then we do it again. At the 1, at the 0, at the -1, at the 0, at the 1. Okay, and you can do it to the negative side as well. And if you look at your transformation sheet, we talked about this yesterday. This is called a horizontal shrink. Now here's the difference between when we did your, like say we did a squaring function. We put the 2 in front of here. This gave us a stretch. Remember when we stretched this? And it gave us your parabola going like this? This was called the vertical stretch, right? But it's also called a horizontal shrink. But at the time I said, don't worry about the horizontal. Just worry about calling it the vertical. When we get to the trig, this is what I didn't want to confuse you in, we call this a horizontal stretch and shrink. So even though this is a whole number here, and it did a vertical stretch, it really did a horizontal shrink. So when we get here, we call this a horizontal shrink. It's like an accordion. You know how anybody remember what an accordion looks like? You know, so when you pull it out, you stretch it. When you push it in, you shrink it. This still we can call a horizontal shrink, but we tended to call it a vertical stretch. Okay? So in trig, we're going to call this guy a horizontal shrink. And I put that on your transformation sheet. When b is greater than 1, it's a horizontal shrink. When b is less than 1, watch what happens when we get a half of this. B is less than 1, we're going to stretch out your curve. Your curve is going to go half of my curve in 360. My curve is going to be half of my curve. So technically, I did a horizontal stretch on this guy. Half of my curve in 360. So I did a horizontal stretch. Does that make sense? We really don't see a vertical movement here. We see a horizontal movement here. Right? Now, let's go to your calculator for a minute. And, the calculator is weird right now. Oh, got it. Okay. We're going to put in just a cosine curve. Cosine x. Now, my mode is in radians right now. If I do a zoom trig, it's going to graph my cosine curve from negative 2 pi to 2 pi. And my table is going to be in radians. Now, when I go look at my table, it's set up in radians, starting at the 0, but I want to see it every 90 degrees, every pi over 2. So I'm going to start my table at 0, and I'm going to increment it pi over 2. You don't have to do this. I just want you to see the difference here. I'm going to increment it pi over 2. So now, see my radians there? See 3.14? This is 90, this is 180, 270, 360. 2 pi is 6.28. 3.14 times 2. It's hard to read in radians, especially when we cut it at 45 or a 30 or a 22.5. It's really hard to read in radians. So instead, put your calculator in degrees. If you change it, you've got to redo your zoom. And now in your table, your window started at 0 and go every 90. So now, here's my pattern. My 0, my 90, my 180, my 270, my 360. Isn't that easier to read than the radians? I like you to think radians when you're putting it on your graph. But in the calculator, I think degrees are much, much easier to use. Agree? Now, if I change this, and do this with me, one weird thing, by the way, is your window. Your window in degrees, your window in radian goes to 2 pi. Your window in degrees only goes to 252. I don't know why. So make this negative 360. It's a positive 360. It just kind of fills the end in. It doesn't really make that big of a difference. And if you only want to look at the right-hand side, just make your min on your x be 0. And just look at the right-hand side. If you just need to do the 0 to 2 pi, just look at that part of it. Whichever part you need to look at. Now, if I now make cosine of 2x, just like we did here, my graph is good. I can see 1 cycle, 2 cycles. I can see my 2 cycles, right? But my table shows me all the 1s, none of the 0s. I get the maxes and the mins, but none of the 0s. Because my difference, my delta, is 90 degrees. What you want to change your delta to is how big is your quadrants. We're going to do 2 curves in 360, which means one curve took 180, right? And in 180, we had to make 4 quadrants. So even though your period is 180 or pi, your quadrants says 180 divided by 4, or pi divided by 4 if you were in radians. So every 45 degrees. So I'm going to change this to start at 0, and my quadrants are going to be every 45 degrees. Now when I look at my table, don't I see all the pieces that I needed? My mins, my maxes, and my zeros? Your delta table has to match the size of your quadrants, or you're not going to see them all. Yes? Okay, now let me ask you this. If I put y equals cosine 4x, how many complete graphs, how many complete cycles do I want in 360? How many complete graphs? What's my frequency? 4. I want to see this thing go 4 times by the time I get to 360. So I'm going to change my y equal, and I'm going to put a 4 here. There's 1, 2, 3, 4. So you go through 4 times, 4 cycles. Now, it might not be so bad for me to get that to my paper. This guy happens to be incremented by 90s. So can you see that my scale, your scale is in your window. See my scale incremented by 90s? That's where your tick marks are right now. Do you see where your graph is at the 90? Every 90, you want 1. See it? Every 90, you want 1 of these. We're only sketching. So is that good enough for us to maybe go like this? Every 90 and make 1. 1, 2, 3. Is it okay for us to do a sketch like that? Yeah, that's not a bad thing. If you want to get that detailed, you're not going to see it in your table because we're set at something different. We have to be set at the quadrants. So if I have to go every 90 degrees and I need to make 4 quadrants, this is where the radians are harder, I need to go every 22.5. I need to change my window, my table set, to go 22.5. And now I'll see all my parts. If you feel you need to see them and you can't figure them out the other way, then make sure you do your delta table. If not, your sketch is probably okay. Every 90, I gotta make another one, right? Kind of get into the swing of that. Are you guys okay graphing on your calculators? I'm not a big calculator person when it comes to graphing trig. I would rather graph this way, but it is whatever it is you like to do. I like you to see that going through the quadrants. I think that makes a big difference. Also, your other transformations work real similar off of this. Let's do, let's see if I have one here. Okay, let's do a vertical shift up to. We're going to take this cosine curve. I think it's at the bottom of this page. Yeah. Is it at the bottom? Okay, yep, there it is. Thought I saw it on here. Now, just like we did with your x squares, your graphing, your quadratics, or your cube roots, or your square roots, we said instead of doing it in the front, you might want to do it in the back. So just take this and put this over here. According to your transformations, this still gives you a vertical shift. You're going to take your curve, you're going to physically walk it up 2 spaces. Now, an easy way to do this is, I didn't change the frequency, so I'm at 1, 0, -1, 0, 1 on every 90 degrees, so that was good. Let's change your y-axis, just change this guy to go to 3 to -3, and put 2 more little marks in here. Okay, we're gonna translate this. We're gonna shift it. Now, an easy way to do this is if you want to walk everybody up 2, add 2 to all your parts. So my pattern will be 3, 2, 1, 2, 3. Just take your maxes, your mins, and your zeros and add 2. So now I start here at the 0 degrees, I'm at the 3. At the 90, I'm at the 2. At the 180, I'm at the 1. 270, 2. 360, 3. Here's my curve. See it? Here was my original curve. I walked everybody up 2, up 2, up 2, up 2, up 2. I made everybody go up 2 units, right? It's probably easier to do it like this than it is like this. And your range was from -1 to 1. And you can probably see where it's going here. Or just add 2 to these guys. So your new range is from 1 to 3. Your amplitude is still 1, because remember, your amplitude is from the resting point. You also moved your x-axis up 2 units. Everything shifted up 2 units. So now your resting point is here. Your amplitude still says 1. So you can still do all your vertical shifts the same way we did the other ones. You can graph them and then move them, or you can take the endpoints, the ones or the midpoints, the max and mins, and graph them that way. Yeah? Okay. And of course, a -2 would bring us down 2 units. One other thing we have in terms of transformations is called a phase shift. This phase shift is very, very similar to when we did this. With a quadratic. Here was your basic quadratic. When we were inside the parentheses, we did a horizontal shift. And we did it the opposite way, right? So we moved this guy 2 units to the right. We basically do the same thing with your phase shift, but we move everything right and left. The whole curve moves, of course, right and left. We call it a phase. And your formula for your phase shift is C over B. B is this guy right here. It happens to be a 1. And it moves the same way as the old ones did. If it's a negative, it moves to the right. If it's a positive and a plus sign, it's moving to the left. So I'm a negative, I'm going to move to the right, C over B units. So here's my C, pi over 2 over 1, which is a shift of 90 degrees to the right. So here's my regular sine curve, 0, 1, 0, -1, 0. And I'm moving everybody to the right. This is moving to the right. This guy's moving to the right. This guy's moving to the right, to the right, to the right. I just shifted my sine curve to the right. And so forth. And I can continue on to the other side if I want to. So you moved everything to the right 90 degrees. Now, if you took your original sine curve and you moved your sine curve to the left 90 degrees, what would you get? Visualize it. Take your green curve and with your eyes move it 90 degrees to your left. What did you get? Here we go here. Here we go here. And my green curve. Here we go here. What am I getting? My cosine curve. Right? Isn't it a shift? A horizontal shift of 90 degrees? It's because don't my quadrants work all zeros and ones? So if one's a 0, 1, 90 degrees later it's a 1, 0. Right? So I have a horizontal shift. I call our horizontal shifts a phase shift in the opposite direction. That's why our transformations for your sines are just for your trig functions are just slightly different. It has the same movement, the same motion, we just call them by different things. Now, normally what will happen is we don't always get a phase shift with a frequency of 1. You can put a 2 in here, a frequency of 2 in here, and you would do pi over 2 over 2. Flip this over, and you would shift it 45 degrees, right or left. You would have a partial shift, a C over B shift. But the difference between us and the honors, I'll keep your B at 1. Because the goal is for me just to get you to see a phase shift. So our B's will be 1. We're going to be moving, I want you to see moving left, moving right, and I want you to see the shift in terms of the C part of it. Because it's harder to visualize it when you change the frequency. So I did it last year a little bit, and it was a little bit more confusing, so it kind of took away from everybody understanding what a phase shift was. So I decided to keep B at 1. B can be other than 1, but for us, we'll keep it at 1, so we can just get the concept of the phase shift, where it's going. Okay? Do you guys have